Presented by myself, Mr. Agbamu. You can see my name over there, Idonogrene. SS2 class. The subject is mathematics, topic surface area and volume of a sphere. The objective of today's class is we should be able to define a sphere, state the relationship between a cylinder, cone, and hemisphere, use the relationship between a cylinder, cone, and hemisphere to derive the volume and surface area of a sphere. Let's start. Now, what is a sphere? The definition I have here says a sphere is a solid shape with perfectly round surface. It is a three-dimensional shape. Examples are orange, football, and so on. Let me show you a little animation of how a sphere looks like. You can see my view here. This view is showing me a two-dimensional view. You can see the y and the x axis, while this view is showing me a three-dimensional view. Because there are some cases where some students confuse a sphere and a circle. Some students think that a circle is the same thing as a sphere. If I pick a circle here, let me show you so that you can differentiate it well. See, it's asking me for radius. Let me take radius 3 for example. So I click OK. So this is just a circle. The circle is a plane shape. It's a two-dimensional plane shape. You can see it even in the three-dimensional view. You can see it's just there, just a normal plane shape having an area. You can see the area it covers, just this space on this floor of this three-dimensional shape here. But if I take this out, let me take a sphere. If I take a sphere on this point, you can see a sphere. So this is a sphere. So this is how a sphere looks like. It's really different from a circle. A sphere is not a circle. But if I turn it to face us in this way, you can see now I've turned the sphere to face us directly, looking at it from the top. Some people may think it's a circle. That's why some students confuse a sphere from a circle. You can see that this is a sphere, though it's facing us directly, and you are seeing something like a circle, a shaded circle. But if I turn it in this way, you will see the solid shape. So this is a sphere, and these are the three dimensions. You can see the x-axis, the y-axis, and the z-axis. So this is how a sphere looks like. So take notes of this. Okay, let's go back to our class. So now that you know what a sphere is, let's see how can you get the volume of a sphere. The volume of a sphere can be obtained by subtracting the volume of a cone from the volume of a cylinder in order to obtain the volume of a hemisphere, and then multiply the result by 2. Instead of memorizing the volume of a sphere, just like what some students do, and at the end of the day they may forget it, why not just know how to get it? And how do we get the volume of a sphere? Just subtract the volume of a cone from the volume of a cylinder. And we are used to cone, we are used to cylinder. We know these two shapes, they are common shapes in our daily lives. But there's a condition in this statement I have here. This is a condition. You say this is only possible if the radius of the cylinder is equal to the height of the cylinder. That's one condition whereby you can subtract a cone from a cylinder to get a hemisphere. Take note of this. Let me show you this animation again so that you understand what I'm trying to say. As it's coming up, let me show you this. So you can see what I have here. This is a hemisphere plus a cone is equal to, we don't know the result yet. What this one is trying to tell us is when you add hemisphere to a cone, or you add a cone to hemisphere, it's going to produce a result. So what is this result going to be? Let me demonstrate it here. Let's see. If I move this slide up, just watch what it will give. You can see the shape that it's trying to produce. You can see as I move this slider upward, you can see that it's giving us a cylinder. So what this animation is trying to do here is, when you add a hemisphere to a cone, you are going to get a cylinder. So this is where that statement I just made came from. This statement that the volume of a sphere can be obtained by subtracting the volume of a cone from the volume of a cylinder. So take cone out of cylinder, you are going to get a hemisphere. Then since hemisphere is half of a cone, since hemisphere is half of a sphere, then just multiply it by 2, you are going to have a full sphere. That's why we say you then multiply the result by 2. Okay, I have another one I would like to show you. So this is another good one that you use to understand what I just tried to demonstrate. So you can see this. You can see this is the cone and this is the hemisphere. So when you add cone to hemisphere, it's going to give you a cylinder. Let me move this slider down. Just watch as it comes down gradually. See, it's coming down gradually. You can see it. Just watch this. It's coming down gradually. See, I'm trying to add both of them together. At the end of the day, you see that this hemisphere is going to turn into a sphere. So with this idea, you don't need to memorize any formula. Just know how it is formed, and that is all. You can see how the cone is going into the hemisphere, and at the end of the day, it's giving us a perfect cylinder. You can see. So hemisphere plus cone is equals to a cylinder. So if you do the reverse now, if you now subtract a cone out of a cylinder, like what I'm doing now, I'm removing this cone out of this cylinder, you see it's going to give me a hemisphere. So with this idea, we can derive the volume of a sphere, and also we can use it to derive the surface area of a sphere. If you observe something here, you will see that the surface area, which is the curved surface area of this cylinder, let me go back so that you watch it very well. Just watch. You can see the curved surface area of this cylinder. See the cylinder that is formed, you see the curved surface. Let me roll it around so that you see what I'm talking about. See, even as I'm taking it around, we are getting the same thing because it's a curved surface. The curved surface of this cylinder, as I subtract it, as I subtract the cone out of it, you can see that the curved surface of the cylinder is turning into the curved surface of the hemisphere. So with this principle, we can simply say that the curved surface of a cylinder is equal to the curved surface of a hemisphere. So this is a good picture that when you put this in your memory, you can see that you don't need to memorize the volume of a sphere. You can easily remember it by just subtracting a cone from a cylinder. You will get hemisphere, then multiply the hemisphere by 2. It will give you a cylinder. So if we go back to our write-up, so that's what we try to do here. Alright, let me put in the formulas we need. So volume of a cylinder. What is the volume of a cylinder? We all know that a cylinder has a circular base, and the area of the base is a circle, which is pi r square. If I put in my pi r square here, so this is pi r square times h, you can see it, times h. This is the volume of a cylinder, but I said that r must be equal to h before this cylinder can be turned into a sphere. For you to turn a cylinder into a sphere, the radius must be equal to the height. That's what I mean by this condition here. This is only possible if the radius of the cylinder is equal to to the height of the cone. This statement is very, very important. If they are not equal, then you cannot produce a hemisphere whereby a sphere can be produced. So this radius must be equal to the height for you to get a hemisphere. So if I replace the r with h in this my first equation here, I'm going to have pi r square times r, which is this. Then finally, the volume of the cylinder that I'm going to use is going to be pi r, then radius square times radius is going to give us radius cube, which is this. I think you can see it clearly. I think it's bold here, pi r cube. Alright, this is the volume of the cylinder we are going to use for our calculation of volume of a sphere. So let's keep going. Now let's look at volume of a cone here. So volume of a cone, how do you get the volume of a cone? Cone is usually gotten by subtracting 1/3 out of a cylinder. In case you don't understand what I mean by subtracting, I'm talking about when you remove 1/3 of a cylinder, you are going to get a cone. Let me just show you in this animation I have here. You can see this is a cylinder. You can see this cylinder. You can see this is a cylinder. If I remove 1/3 out like this, just watch what I'm going to show you now. I remove 1/3 out like this. Yes, take this, sorry, let me get my planes, let me view it very well, sorry. Okay, alright, okay. So if I sketch this part like this, see what I'm going to do, just watch. Okay, so this is what I'm saying. So you can see my cylinder. What I'm doing now, I'm removing 1/3 of the cylinder. You can see that a cone is being formed. So this is how a cylinder is being formed. So that is why we say the volume of a cylinder is 1/3 the volume of a cone. You can see it. I just removed 1/3 out of it, and you can see that a cone is formed, which is perfect cone. So take note of that. You can see that this is a cone. So with this idea, if I go back to our note, you see that this is the volume of a cylinder. So the volume of a cone is gotten by removing 1/3 out of this. So all I just need to do is to remove 1/3 out, which is 1/3 of the volume of a cylinder, pi r square times h. But remember our condition, the radius must equal to the height. So therefore, we are going to get volume of a cone as 1 over 3 pi 1 over 3 pi r square times r. Then finally, okay, sorry, let me move this upward a little, sorry. Okay, then finally the volume of the cone is going to be 1 over 3 pi r raised to power 3. So this is the volume of the cone. You can see it. The volume of a cone is 1 over 3 pi r cubed. Since the radius is equal to the height, so we don't need h. Just remove h and put r there. So now, how do we get the volume of this hemisphere so that we can finally times it by 2 and get the volume of a sphere? So we say the volume of our cylinder is this and the volume of the cone is this, and the condition we state here is subtracting the volume of cone from the cylinder. So all I just need to do here is to say pi, which is volume of the cone, volume of the cylinder, pi r cube minus pi r, minus 1 over 3 pi r cube. Okay. That's volume of cylinder, pi r cube minus volume of cone, 1 over 3 pi r cube. Then if you factorize, our pi r cube is common to both terms. If I bring it out, I'm going to get something like this: pi r cube 1 minus 1 over 3. Then if you move the next stage, you're going to get pi r cube. You simplify this bracket, you're going to get 3 minus 1 all over 3. You can remember your simplification. The LCM is 3. 3 divided by 1, 3 times 3 is 3, minus 3 divided by 3 is 1, 1 times 1 is 1. So that's what I did here. Then if I move on, I'm going to get pi r raised to power 3 open bracket 2 over 3. Then finally, my volume of hemisphere is going to be pi r, it's going to be 2 over 3 pi r cube. So this is the volume of a hemisphere, 2 over 3 pi r cube. That is it. Then now that I have my volume of a hemisphere, and hemisphere is 2 times, a sphere is 2 times hemisphere. Hemisphere is half of a sphere. So all I just need to do is to multiply the hemisphere by 2. 2 2 times 2 all over 3 pi r cube. Then my final volume, therefore the volume of a sphere is going to be 2 times 2 will give us 4. Sorry, I need this one. Give us 4 over 3. 4 over 3 pi r cube. So this is the volume of a sphere. All you need to do is subtract the volume of a cone from the volume of a cylinder to give you the volume of a hemisphere. You can see it's very correct and accurate. You don't need to memorize all these formulas. Sometimes when you memorize, you may forget them, and when you forget it, it may cost you in your exam. Just remember this condition: the radius must be equal to the height. Then the radius, just replace the height with the radius. You can see it, replace height with radius. That is all you need. And subtract and solve down. You will get your volume of the hemisphere. Then from there you get your volume of a sphere. Take note of that. Then how do you get the surface area of a sphere? You remember the animation I showed you? The surface area of a sphere can be obtained from the curved surface area of a cylinder. All you just need to do is the surface area of that hemisphere. Let me show you again. That hemisphere that was turned into a cylinder. Well, when you put this inside, remember when you put this inside, remember when you put this inside, this surface area, the surface area of this hemisphere is going to be equal to the surface area of the cylinder that is going to be formed. So since they are equal, why not just equate them and you get your surface area of your sphere. So that's what we are doing. And what is the surface area of, and what is the curved surface area of a cylinder? It's very easy. The curved surface area of a cylinder is 2 pi r h. 2 pi r h. That the 2 pi r is the circumference of the circular base, then multiplied by the height of the cylinder. So this h is the height of the cylinder. The radius, the r is the radius of the cylinder. So since you have this, then now we say r must be equals to h. Then you now have your 2 pi r times r. So the final curved surface area of a cylinder that we are going to use here is going to be 2 pi r squared. 2 pi r squared. So this is the formula, the curved surface area of a cylinder, and it's equal to the curved surface area of a hemisphere. You can see it here. The curved surface area of a cylinder is equal to the curved surface area of the hemisphere. You can see it here. Both of them are equal. So since they are equal, all I just need to do is to multiply by 2. Just need to times this by 2. All I need to do here is 2 times 2 pi r squared, which will finally give me this result, which is 4 pi r squared. So 4 pi r squared, this is the curved surface area of a sphere. Then the curved surface area of hemisphere is also equals to the curved surface area of a cylinder, which is 2 pi, which is 2 pi r squared. That is it. But when you need the total surface area of a hemisphere, we are talking of the general total surface. I know hemisphere has, let me show you here. The total surface area of hemisphere consists of the base, which is a circle. You can see the circular base, and the body, which is a curved body. You can see it. It have a curved surface, and the bottom, which is a circle. So you add this base, circular base, plus this curved surface. Take note of that. So the circular base is just normal area of a circle, so which is pi r square. You add it to this curved surface, which is 2 pi r square. So this is the curved surface area, total surface area of hemisphere. Why this is the curved surface area of hemisphere. So with this,